My last talk here, and I really enjoyed staying here because actually I have difficulty to give talks about minimal surfaces because I usually do not give talks to mathematicians. I started working on minimal surface like in 2017. And for about 3 years, I only give talks to biologists and material scientists and so on. And so this is strange. And I also told you I was not doing minimal surface before. Before 2017, I was working on polytope theory and sphere packings. And so this talk will be informal. It will just tell 2 stories of how I began to work on this topic. So this is starting that I always give before giving a talk to scientists. So because I really had an experience of how difficult communication is. Not only communication between different disciplines, even within mathematics, even the disciplines themselves, like statistical physicists and soft matter physicists, they argue all the time and they hate each other. I really met people who say the harsh word towards each other. But anyway, TPMS is still a topic, minimal surface, especially those triply priority ones. They are still a topic that they really get interdisciplinary. Because when people say interdisciplinary, it's usually fake. It's just I put my result and your result into the same paper. That's all. But TPMS is a rare example where physicists did real contributions to mathematics, and the mathematicians did contribution into physics. They really interact, although they hate each other. So minimal surfaces in nature, it's actually everywhere. So from a mathematical side, I want to abstractize everything. So in my opinion, what is happening is that every time you have conflicting interactions between objects, then there will be possible, it's possible that there will be a minimal surface. So for example, in the first picture, we have a butterfly, and this butterfly is fantastic because you look at the wings from different angles, you see different colors. And that is because there is a gyroid on the wings. And then you have these cells. And I believe these 2 phenomena in the biological, so they call biofilms, they are the same phenomena. So what was happening is they have molecules with a head and a tail. And the head loves water. And the tail hates water. So these are conflicting interactions. And if you put this thing into water, I imagine they did your experiment by putting these molecules in the water, shake it, put it still for a week. And that's what I understand from their paper. So I'm not a physicist, but it ended up with 2 molecules, tail to tail. And goes like this, forming a surface. So they call this, so in the middle, turns out to be a minimal surface. So they call this bilayer because this is a layer with 2 layers of molecules. And I will explain, so why this could go to a TPMS. So, and there is an example that I didn't go into it very deep, but this is a neutron star. And in neutron stars, things are very, very dense. And if you consider the protons in the neutron star, protons are positive. So first, they have a electromagnetic interaction, electrostatic interaction that repulse each other. But then when they are very, very dense, they are very close. And at some, when they are close enough, there is this nuclear interaction between them. That's interacting. That's attracting. And then turns out that they will go attracting, so a lot of positives. And here, another layer go attracting with each other, but they repel. And this is another conflicting interaction between particles. And this it turns out also form a structure that can be modeled by triple pyramidal surface. And it's called nuclear pasta. And I don't think they really see it in experiment. I think it's only numerical. They did numeric experiment.
It's probably a local kind of thing. It just kind of, because things are chaotic, right? So locally you have a structure, but then the structure doesn't go very far. I'm guessing.
Yeah, I cannot answer you, but from the experiment I see, they can control the condition so that there is a large region of uniform
But in a nuclear star? No.
No.
Experiment in the laboratory.
Right. You know what I'm saying? In a nuclear star, I'm guessing it's a local. You sort of get it, the structure, and you kind of disappear. You get the structure.
Well, I imagine that when the density is uniform, there could be a uniform environment for a large region of gyroid to appear. But how large is large? I mean, for neutron star, like kilometers is possible. Okay. Yeah. So anyway, it is everywhere. So here is the history of contributions from scientists. First, gyroid is not discovered by mathematicians. Chen was a NASA scientist who seems to be bored and did a lot of model making. And okay, good. And actually, I see his models, and that's even, I think, very clever. That can be used for today's 3D printing. And Matthias Weber inherited all his models now.
It's plastic models.
Plastic models, yeah. And
let me ask you, did you ever try to bend the little piece of like a?
No, it's very fragile now. I dare not to.
I
dare not to. It's very fragile now. And then in the 1980s, there is a Nature paper. There is a Nature paper who says that we can use minimal surfaces, all those Schwarz structures and the Schoen's gyroid, to model the so-called bicontinuous structure. So that's definitely not a name by mathematicians, because bicontinuous, they mean connected. So bicontinuous structure is a structure where one surface, one connected surface, divide the space into two connected components. So this cannot happen. So in dimension 2, such a structure must be very easy. It must be a Jordan curve and dividing into two simply connected case. But in dimension 3, you can have a connected surface that divides your space into very complicated topology. So
this is what crystallographers call labyrinths.
Lave graph is a way to describe the bicontinuous structure. Yes.
I've seen papers by Fisher-Koch.
Oh, yeah.
They call labyrinth.
Labyrinth. Yeah, labyrinth, because it looks like a labyrinth.
Yeah, yeah.
It looks like a
PPMS.
Yeah.
Divided into two regions.
Yeah. And so I told you we have Schwarz, gyroid, and mixed families. And then most new examples. First, Chen find a lot of new examples, I think 14 of them. And most other examples were found by Fisher-Koch because they really learned and understood Kakia's the conjugate Plato method. They learned that. And conjugate plot method is simply rotating around straight lines and reflecting. And so, question, we are mathematicians, we know group theory. And do you know how many space groups are there? So how many groups for three-dimensional lattice are there?
107, 200, 128, maybe some number.
400.
Yeah, close, but must be wrong.
224. There's some kind of number.
How many?
Some
200.
230,
24.
230, I think that's
230.
yeah, 230.
Yeah, I'm trying to remember the number.
Yeah.
Crystallographic groups.
Yeah, and crystallographers, they know each one of them by heart. So when they see the conjugate plateau method, they say, okay, we are very good at this. So they get, I think they get dozens of, I think tens and 20s, 30s of new examples. And they are very good at it. And many of them are still studied now because their structure is very interesting. And
but a focus might also be not always, but sometimes on stable examples like the gyroid. It's in terms of where you want to preserve volume preserving, then they actually have they're stable, right?
yeah.
With respect to certain deformations.
Yeah, and then we have a lot of physicists, including Heider and Schrödinger, who's still active today. They visualized many mixed surfaces because I said if you want to, if you ask me to give you an example in mixed family, I will give you a Schwarz, one that Schwarz already knew. But they managed to visualize many monoclinic deformations of mixed surface. And also they find the gyroid deformations. And okay, now today, if you Google triply parallel minimal surface, you won't find math papers. 99.9%, most of them are by physicists. And most of them are not very deep in math. Because those who find visualize mixed surface and gyro deformations, they actually understood complex analysis. And you don't find a chemist who understands complex analysis today. But all there now you can find a lot of papers about mechanics, about self-organization, about biology, about how it can be used to transport medicine, for example, about how the color of the butterfly wings looks different from different angles, and so on. And these are consist of absolutely most of the papers on triply parallel minimal surfaces now. And math papers, I know a dozen, but that's all. For others, I think there are thousands of papers per year. There's a lot. So, story A, the twinning defect. So, this is my wife, and she's the hero in all my work, actually. So, the story is she's working, she's master was about material science, nanophysics, and she's working with a colleague called Han Lu, who's a professor now in Shanghai. And they were looking at a structure that they generated like this. Put some molecules in the water, shake it, put it still, and before observing it, they managed to replace water by some silicon material so that this becomes hard. So they can cut it and observe it in microscopy. And they see something like this. Okay, then they use the X-ray to observe it, and X-ray is used to analyze the structure of crystals. And they say, okay, on each side, I have a Schwarz diamond surface, Schwarz D surface. And so, I mean, this picture, on each side is a Schwarz diamond surface. But in the middle, there is a non-trivial reflection plane. This is not a reflection plane in the Schwarz D surface, but we have two copies of D that is connected by a reflection. And then they also observe this. We know gyroid has no reflection, but they observe that we have on each side a gyroid structure, but then in the middle there is reflection relating them. So this kind of structure for crystallographers, they are known as twinning because you have a twin of the same thing related by a reflection. And my wife was using a software called Surface Evolver. And they say, okay, maybe we can use Surface Evolver to model this structure. So they asked my wife to help, but they didn't succeed because they put the structure, they put a model of the structure in the computer and they tried to minimize the total area. Then the computer broke. They didn't understand why. And the mathematical question arise from this problem is, can a TP mass still be minimal after I put a twinning boundary into it? So this is the question. Anyway, they didn't solve the question, but they went to a conference presenting a model, a picture where they just smooth the boundary. And but then this is a very nice conference where they gathered physicists, material scientists, and mathematicians together. And then all the mathematicians there just protested. So, are you sure this is still a minimum surface? Then she answered, no, we are not sure. And our simulation didn't work out. And then she talked with Carsten, also Baumann. And Carsten explained to them that actually minimal surfaces do not minimize global area. And triple minimal surface is a typical example that actually if you take a parallel surface, meaning you move all the points on the triple minimal surface along the normal vector by the same value, you get a parallel surface and its area is actually smaller than the triple minimal surface. So the area is not, but then then they asked, so my wife didn't understand. Then she asked me to help. That's how I get involved. And I instead minimize the so-called Wellmore energy, which is the integral of squared mean curvature. And if I can minimize this to 0, it means the mean curvature is 0 everywhere. And I get a picture of this gyroid, the twinning of gyroid. Actually, for both the diamond and gyroid, I can minimize the mean curvature down to 1 to the 10 to the minus 26. This is very, very low. So it means that it is strong evidence that we can twin the minimal surfaces, and it is still minimal. But this is only numerical. And if you ask me today, I think the D twin, the Schwarz D twin is real. This is really minimal. But the gyroid twin is not, because actually this I'll talk about it later. And but if it's not a minimal surface, it's still good, because for applications, the biofilms, the bilayers, they are flexible. It can tolerate a little bit small mean curvature. So it is still good. And actually, we already have 3 other groups who comes later, but they also observed the twinning of gyroid in their experiment. Okay, then the thing is, I had numerical evidence, and I want to prove rigorously that we can indeed twin the minimal surfaces. Then I begin to learn the node opening construction. And as I said last time, for each flat Q-torus, there could be at most 5 balancing positions for the nodes. And the consequence is, I'll first give some examples of triple minimal surfaces. So if you have this is any torus, if you stack the nodes like always by the same vector, you get mixed family, and in particular, if you have a square and you stack first layer here and second layer in the middle and third layer still on the corner and so on, you get a tetragonal P surface. And if you have this thing, rectangular, and first layer here, second node here, third node here, and so on, you get CLP. And then you have this example. So this is 60 degree. Then first layer at corner, second layer middle of triangles, third layer same thing, and so on. You get the rhombohedral P and D surface. And then these are mixed family, and then we have this still the triangle lattice. First layer here, second layer here, but third layer back. So zigzag, go forth and back. This will give you Schwarz H surface, and deforming it will give you the new OH surface. And the last one is new. So for any torus, we have 3 trivial balance position at the middle of edges and the middle of the parallelogram. And they are trivial balance positions. And I didn't know this, but I become to know this by looking at the gyroid. I cut the gyroid because that's the 6th order rotation symmetry. I cut the gyroid by these planes and I look at these planes. Then I see these circles. Then I say, okay, if I have circles, it might come from some node opening. That's just a pure guess. I have no idea how node opening works at the time. And it turns out I calculated, and it turns out that if I put nodes at these positions, they are indeed balanced. So consequence, I have 5 symbols, but the interaction is only between adjacent layers. So if I have the first layer and the third layer, they do not interact. Therefore, for each layer, I have 5 choices. So that is what I said last time. Any bi-infinite sequence of 5 symbols gives me an example, a family of minimal surface. That's the quantity of real numbers. And most of them are disordered. There's no order at all. And but for the twinning I want, it's just a special case because I have so it's still the triangular lattice. I go always this way because that gives me D surface. But at some point at the twinning surface, I come back. I change the direction of stacking. That's how I get, so I explained that the twinning arises from stacking fault. And this is actually good for physicists because this kind of stacking fault they are very familiar. In this context, you have spheres, like when they are going to war, they put a lot of cannonballs in a very dense way. And how to put them in a very dense way? You put the first layer into a triangular lattice. Not a very good drawing, but then you put the second layer in the hole of the first layer. And then for the third layer, you have choice. You can keep going in this direction, but then you can always have a choice to come back. And the density remains the same, actually. And then I also noticed that gyroid might also arise from Catenary limit. Okay, this observation is also needs to a new thing because before if you want to draw a gyroid, these biologists they want to draw a gyroid, they either use a approximation formula that's sine x cosine y plus something, this very simple formula, or they go to custom water power mine in Darmstadt because custom has a fire that you can put into the software surface evolver and give it. But this file is almost written by hand. This program is almost written by hand. But now I have a new way because I have a new point of view of gyroid. I say they are obtained by node opening. So I very naively get this configuration. I open one node here. So I have a rhombus, as I show on top. I have a, that's the first layer. So I open one rhombic 2 between the first and between 0 and 1, and another rhombic 2 between 1 and 2, and goes like gyrating like this. And I put it into surface evolver, and boom, this is gyroid. I check, this is gyroid. And then I begin to play with it. If I can do it with rhombus, I can do it with any parallelogram. And so I do it with a square, for example, and a rectangle, for example. And this is how I find another, the first explicit bifurcating branch of from the TD. So this is how I discovered it. And that's the beginning of all my discoveries later on triple surfaces.
You implemented this in one evolver by minimizing on the quotient.
Yeah, minimizing the well-known energy in the quotient. Yeah, and also this is still a conjecture that a gyroid can deform like this to a catenoid limit. I didn't prove it yet. I only proved it for rectangular lattice. And then I read in the physics paper. So they were wondering how the TPMS appear in nature and in experiment. Because if you have very few molecules, they are just layers of bilayers. But now then they develop into very complicated bicontinuous structure like this. How does that happen? So they have a theory that different layers, they first touch and form a small node. It's exactly the node, like in mathematics. And they draw a picture like that. And I say, well, then how did TPMS appear? Because at this point, we know, mathematicians understand the interaction between the nodes. So maybe the arrangement begins exactly at this point. And then the node opens and into a minimal surface. So that can be developed into a physics explanation. But I still have difficulty to convince them because I'm not a physicist and I still cannot use physics language to describe the interaction between the nodes yet. And then, so why triple paraminimal surfaces are good? So one of the theory is that first I need to decompose. So I tell them that it is not because of the tension, surface tension, because surface tension tends to keep the area minimized, but triple paraminimal surfaces do not minimize the area. So what is the driving force? So one theory is that the molecules here, this molecule, it has a length, and it might have a big head. So the shape, it has a length and it has an angle. So the length, it doesn't want to change a lot, and the angle also doesn't want to change a lot. So the angle will give it a so-called spontaneous curvature, and this gives you a mean curvature. And the length, what you can consider as a screen. So if the spontaneous length is L, I want this thing to be small because the doesn't like to be stretched or compressed. And I also want the mean curvature also not far from the spontaneous curvature. So if you put these as energies, this is the theory that that TPMS would occur. So if you minimize these two things, the variance of length and the variance of mean curvature, basically the variance of shape, then you will get a TPMS. And before, they only managed to model this model. So this, if you have the length being 0, you get parallel surfaces of triple surface. And if you say the mean curvature is constant, you get the constant mean curvature surfaces. So that was the two dominating models for the triple surface with a thickened mineral surface. And here I worked with my wife. That's the only paper that I collaborated with my wife. But in this paper, we combined them together. So we modeled a weighted sum of these two energies. And it turns out that it works better than any pure model of them. And this collaboration was terrible and almost cost me a divorce. Never work with your family. I mean, for example, all the mathematical analysis was put in appendix, and she says that is the thing to be done. And I also had a fantastic title, and it turns out to be a title of 3 lines, something like that. And yeah. And then there is another problem. So yeah, we know that triple minimal surfaces are good, but then in experiments we mostly observe gyro, and we often also observe diamond and primitive surfaces, but all others are much more rare. So why these GDP are the best? Of course, GDP is best, but yeah. So one theory is that they minimize the variance of Gaussian curvature. So how is this reasonable? So we want to, this is so-called health energy. So right here. So what is this theory? So I want an energy, and this energy is about the curvatures of the surface. So what do? I take the first order term, which must be linear, then this must be something related to mean curvature. Second order term, it's second order that must be related to the Gaussian curvature. So, and so on. And mean curvature is 0. Second curvature, Gaussian curvature integration is a topological invariant, so doesn't matter. The third order term also related to mean curvature, 0. And the fourth order term, okay, we have Gaussian curvature squared, so variance of Gaussian curvature. That's how physicists often argue, yeah. And but anyway, so they guessed that the variance of Gaussian curvature would play a role. So they tested all the examples that they know. For example, this is a test of the rhombohedral gyroid and the rhombohedral P and D surfaces. And they see that, well, indeed, the 3 surfaces are minimizers of variance of Gaussian curvature. And now I'm more interested in the triangle here because that's normalized by the average Gaussian curvature. So this they have the same value here because Gaussian curvature is because it's an isometry. They are in the same isometry local isometries. G, D, and P, they are in the same associated family. So they have the same value at the triangle line. So I try to prove that indeed, if I have the flat points, the branched values, pointing towards the vertices of a cube, then I will have minimizers of variance of Gaussian curvature. This is in the plan.
So you want to distribute the Gaussian curvature over the surface, right?
Yeah.
So it's not too concentrated. So it's too concentrated.
Not too concentrated.
Concentrated corresponds to nodes.
Mhm.
Right?
Yeah. So that's their theory. So Gaussian curvature is most uniform.
As opposed to being.
Yeah, it's closest to.
Okay. Nowhere have you mentioned the fact that these are stable with respect to volume preserving deformation. And they're flat toroid.
Yeah, because that's another group of physicists that
Right.
they prefer.
Look at volume constraints.
Yes, they prefer. Well, I will have another one who's interested in this because they have biofilms that enclose some material,
Right.
like nutrition and so on, and they want to assume that this volume is preserved, and then how the surface deformed. Yes.
Just to mention, like maybe not people everyone doesn't know that, but if you take a genus 3 triply periodic minimal surface, so then it divides space into isometric regions. Any genus 3 minimal surface, triply periodic, separates R3 into two isometric regions. So particular, like same volume, all the same invariants.
Yeah.
But they glue together and make R3.
Yeah, they also call it balanced.
They what?
They also call it balanced if it divides the space into two isometric components.
Yes.
Yeah, and
But any genus 3.
any genus 3. And first, the non-example is genus 4, the IWP.
Right.
Yeah.
And it doesn't divide into equal volume.
No.
Say again, for genus 3, any example is balanced.
It's balanced in the.
Genus 3 separates R3 into isometric pieces.
Not for your family,
Any
one.
any example. Actually, because if you take any zero Gaussian curvature and you invert through that point, x goes to minus x, that leaves the surface invariant and separates the two regions. You take one region into the interchanges of the two regions. So invert through any zero Gaussian curvature, then that preserves the surface and that's because the Gauss map is 2 to 1, and you're just looking at the flip the 2 points with the same normal vector. You look at the equation.
You exchange the two branches.
Yeah.
Okay. Now it's a recent work that Hanlu they do experiment and they see a lot of interesting structures. And this is a structure where you have gyroid on the top and a diamond in the bottom. And there is a transition from gyroid to diamond. And this is not possible. I mean, it cannot be minimal. No. But then we can still do something. So I said, okay, the torus that I used to open node for diamond is 60 degrees. And the torus that I used to open node for gyroid is still conjecture, but it's 70 degrees. 10 degrees is not very much. So I say, might they go like just deform a little bit afterwards? After all, they are soft matters. Well, so I give this theory. So I say I compute all the diamond, but I deform the torus from 60 degree to 70 degree here. And I also deform the gyroid from 70 degree to 60 degree. And I find a place where their variance of Gaussian curvature, which is a phenomenological energy, is the same. So this is the theoretical point that they would transition between each other. And turns out, yeah, here is a 65 degrees, something like that. But so this is an explanation of how diamond can be transitioned to gyroid. And this and I choose that point because that's the lowest energy barrier. And then, okay, I got disordered stacking of nodes, and I also wanted to get some disordered line defects from into minimal surfaces. And okay, that's the first. Okay, might be that's the first. Okay, story B: parking garage and helicoids and vortices. So the thing is, someone. So his name. So I should write his name. So Greg Huber. He was a deputy director of a very famous physics institute, and now he's working in the Zuckerberg Chen biohub. So this is the Zuckerberg, so Facebook laboratory, and he's working on biology here. And there are also this is also interdisciplinary institute, and he and his colleagues. They were looking at biofilms, so some structure in the cell, and they see this kind of structure. So they call this Tarasiki ramp. So Tarasiki is their leader, and also they call this parking garage structure. And but Matthias Weber says to me that parking garage is he used the word first. I don't know who called it who. And so they observed the cell structure, and then some astrophysicists, they did simulations, I believe. They cannot go there and see it, no? So they did simulations and see this structure in neutron star. And it's exactly the same structure. So they were very excited and published several papers on them, analyzing them. And then he heard my work on triple barrier surface. Then he visited me in Göttingen and say, okay, I really like to see how the garages, the staircases interact. So I say, well, I know that Chen and Weber, they have a paper doing helicoids together. So maybe we can do something. It turns out a student of Weber was also doing this thing. And but then I noticed something extraordinary. So if we want to glue helicoids into minimal surfaces, the positions is exactly given by vortices in 2D fluids that under their interactions move as a rigid body. And so for that, I need to give explanations. First, the vortices can rotate as a whole. So example, if we put vortices on the vertices of a polygon, and then they will rotate as a whole. And in this case, the corresponding minimal surface is invariant on the screw motions. And this is, for example, the one constructed by Matthias Weber and Martin Krzyzek. It is an example. And Weber's student, Daniel Frieser, is also working on such examples. So screw motion invariant minimal surface. And then the vortices can move together as, translate together as a rigid body. Example, one clockwise, one anti-clockwise, same strength. And these two vortices you can create it by placing a plate in swimming pool, and just do this, you will see two vortices moving together like this. And this will give you a minimal surface invariant under a translation, but this translation cannot be vertical. For example, moving together two vortices, what does that correspond to? The Riemann example. Yeah. And then periodic stationary. So periodic is important because stationary somehow doesn't work. You cannot have a minimal surface with vertical translation. I didn't understand why. We have finite translating vortices, for example, single one. Yeah, the trivial example works. A single vortex doesn't move. A single helicoid, vertical translation. And then I have actually this example. This is also stationary vortex configuration, but construction fails. There is one period that I cannot close. I'm very frustrated by this. But if you have
spinning the outside spin the same way,
the inside spin,
the opposite way,
this is positive,
positive, negative.
negative. I have infinitely many examples like this.
But you said
None of them close.
in the period.
Yeah, there is one period that they don't close.
It never closes. It doesn't close. It can't be
So
closed.
there might be another example that close. So anyway, my construction doesn't work on these examples. No. But if you have periodically arranged stationary vortices and they do not move as a result of their interaction, then we have a vertical translation. And example include many triplet periodic ones, like the RPD.
Yeah, and the shared column because of the surface can be focused doing.
Yeah, all the KMR's examples is one period.
And limit to be part of right structure.
I'll give you pictures. So, and another annoying thing is all the constructed examples admit a orientation invariant symmetry. Like, because the helicoid, you have a translation that reverses the symmetry. And so actually I was working in parallel with this student, Daniel Fraser, and I didn't assume this symmetry. And I wrote a very complicated construction. And he assumed this symmetry, comes up with a very simple construction, Green construction. And then I checked mine, and I cannot prove that mine doesn't have this symmetry. And actually, if his construction works because of uniqueness of the implicit function theorem, all my examples also have this symmetry. So can I get rid of this symmetry? I always want to get rid of symmetry. And this is still an open problem. Okay, examples.
You say the orientation invariant is orientation reversing or what?
Reversing, orientation reversing.
Yeah, reversing. The case the case where you control and you say anything works is when orientation reversing max exists.
Yeah.
Right.
Yeah.
So for you, parking arch means that you have a sequence of minimal surfaces converge into this lamination structure.
Yeah. And some examples. So first, one example found by Tuzet and Weber correspond to a vortex configuration known in 1885. That's a lot of years.
Are those the ones given by zeros of Hermite polynomials?
Hermite polynomials, exactly. Actually, the 1885 already used the Hermite polynomials. That's why interdisciplinary they should talk. And and then this twisted Kaken Shirk tower is you have vortices on the polygons, on the polygon vortex. And here I give a triangle example, and these are experiments in the superfluids, so the quantum physics experiments. And actually, in 1880s, they already have experiments with magnetic disks. And you have a big magnetic there, and you have magnetic disks there, and you manage to keep the magnets stationary. And that's how they did experiments. And here it's mathematical analysis was done by Thomson, and Thomson did this. So so in physics they have a notion of degeneracy, means that if you perturb the configuration, do they diverge or do they converge? Thomson proved that if you have vortices at points of a polygon, but if it's a six-gun or less vortices, then they are stationary. So if you perturb it, they will converge to the original position. If it's 8-gun or more vortices, they will diverge. But either converging or diverging for mathematicians, it means non-degenerate. And only one example is open, the 7-gun. And turns out that it's they call it neutron. I don't remember that. For mathematicians, the 7-gun is degenerate, so you cannot use the implicit function theory.
A particular 7-gun or
particular 7-gun. the regular 7-gon. And actually, there is a recent work who proves that if you don't use linear perturbation but non-linear analysis of the perturbations, the 7-gon is also so if you use a perturbation, it is also convergent. And this means that we can use.
So if you do homotheties, is that what you mean? When you say linear, you mean what?
They just rotate and linear means that I give you a perturbation.
Divide out by.
Yeah, I use the matrix.
Homotheties and rotations.
Yeah. And so anyway, so for 7-gon we can still use another higher version of advanced version of implicit function theorem and prove that we can still open those and so on. And the reminder is that the history should be a pair of vortices. We know it from the beginning of humanity. And Cache rock mix example. Common vortex streets, very famous example. And they move together as a rigid body. And this, for triplet barrel, we have very rare photos, but this one is one that I found very beautiful, fluid dynamic photos. And this one is one that is new. So physicists knew this example for already 30 years, 14 years. And we have, for minimal surfaces, this is new. For each triangular number, so here we have 6, 1, 2, 3, 4, 6 blue, 6 red. 6 is a triangular number. And for each triangle number, we have an example.
But this, like a minimal surface, not like a Viking arch, but the elements in the sequence that converge. Okay, those have planar ends, like Riemann.
Those are planar ends.
Planar ends.
Yeah, like Riemann. So
are they closed periods? I mean, it says at the ends.
Yeah.
It's not like the triplet periodic.
No, it's singly periodic.
This is singly.
Yeah, it's singly periodic.
So it could be one of these. I don't know. Seems to have a planar symmetry. No? Yeah.
Yes. So actually, the degeneracy of this configuration is only so it is only non-degenerate if I assume the vertical and the horizontal symmetry between the vortices. Otherwise, it doesn't work. Yes, a remark. This non-degeneracy is not proved by me, but proved by others in the PDE context, not in the minimal surface context. And also the theorem that each toric ring function has either 3 or 5 critical points. This is also proved in the PDE context, not the minimal surface context. But also, we published similar results in parallel, but because we didn't talk to each other, even within mathematics between different branches. And then after I give this vortices and helicoid paper, I put it on preprint, applied preprint. So Randall Damian, he began to contact me and want me to give to communicate with them, because they for years from 1990s they tried to glue helicoids together, because for them the helicoids means screw dislocation defects, as I show here, and they actually analyzed the some KMR examples, glue them together, and so on. And they want to know my technique, and in the hope that they can understand the physics of biofilms better. And this is a developing chapter. Okay, that will be the end of my talk.